Hi guys, my name is Lucy and I'm a photographer and sometimes a filmmaker, and I really like math. I don't really like science, but after researching everything that's gone into this video, I can attest sometimes science is fun. So today I'll be explaining how to derive the depth of field equations. Let's get right into it. So what is depth of field? Because if we're going to be deriving the equations, we're going to want to know what it is first.
Depth of field is the range of focus within an image, and it can vary based on a number of factors. More on this in a second. You can have anything from a shallow depth of field, a smaller range in focus, which means that the background or the foreground is a lot more likely to be blurry, or a deep depth of field, a larger range of focus, and more of the image is going to be sharp and appearing in focus.
Okay, before I go on, I need to give a bit of a backstory consisting of these simple facts. 1. Light is a wave, an electromagnetic wave to be specific. But when we make geometric calculations, we model the light as rays. To determine where an object's image will fall into focus, we create ray diagrams by drawing rays from the object to the lens. Once these rays reach the lens, they are refracted by the glass at an angle determined by the angle of incidence and properties of the glass. Using Snell's law and the thin lens approximation, we can determine where an object's image is formed based on where the rays converge. Usually we draw 3 standard rays when creating a ray diagram, although only 2 are required. If this convergence happens on the sensor or film plane of a camera, the image is in focus. Thus, for a given lens, when focused for a specific object distance, only objects placed at that distance will technically be in focus, even with the smallest aperture and widest lens. In this case, the sensor or film plane sits at the true focal planes for that lens and object distance. Any object captured not at the distance will technically be out of focus. Then you ask, how does Ansel Adams create landscape photos where the whole wide world is in focus? Well, the range of focus depends on a lot of factors, and when we say range of focus, we mean range of acceptable focus. The farther captured image moves away from the true focal point, the blurrier the object appears. The technically blurriest dot that is still considered within the range of acceptable focus because it is perceived as a sharp dot by the typical human visual system is called the circle of confusion. The circle of confusion can depend on a lot of factors, such as the pixel size of your sensor, the grain size of your film, the scale on which you would be viewing the image or video, etc. The circle of confusion is one of the factors that can affect the depth of field. For example, the smaller the circle of confusion, the shallower the depth of field will be. So the other 3 factors that are going to be affecting our depth of field is first aperture, so that's how wide your lens is, and then focal length, and this is how far the focal point is from the center of the lens. It affects how zoomed in the image is. And then 3, the object distance, which is measured from the center of the lens. These will be our variables in our depth of field equation, unless of course we know our hyperfocal distance. So what is the hyperfocal distance? Well, if you take your camera and you focus it at this distance, everything from half of that distance until infinity will appear in focus. Basically, it's going to be your largest range of focus, and we can use simple geometry to determine this equation.
We start out with our thin lens, a principal axis, and 3 planes, our object plane, the lens plane, and the image plane, where the sensor or film is. For the first ray, we draw one parallel to the principal axis. When it reaches the lens, it is refracted and passes through the focus point and to the image plane. The second ray passes directly through the center of the lens. The image forms where the 2 rays meet, which, because we are setting it up to find the hyperfocal distance, is on the film sensor plane within the circle of confusion and is therefore in focus. Okay, cool. So we know where the image is going to appear, but we're actually solving for the distance between the object and the lens. Lucky for us, these 2 rays we've just drawn have some similar triangles with the ability to help us solve for this distance. The diameter of a lens is how wide open it is, and therefore how much light it lets in. It's related to f-stop or f-number, what photographers and cinematographers use to control their lenses, with the equation diameter equals focal length divided by f-number. Since this is a 2D diagram, the diameter is the length of the lens. In the first triangle, one side is half of the diameter and the other side is the focal length. It's similar to this triangle, where one side is half of the circle of confusion value and the other side is x minus f. We use x as it will help us with our next set of triangles. When we solve for x here, we get this. Then we use our second set of similar triangles to solve for h. However, we want it in terms of an f number, so we can substitute d for f divided by n. And there we go. the equation for the hyperfocal distance. We'll use this equation to eventually simplify our depth of field equations.
There's one more thing we need to know before we start deriving the equations. It's called the thin lens equation. I'm not actually going to derive it here, but it follows similar geometry to what we just did with the hyperfocal distance. Essentially, it says that 1 over the object distance from the lens plus 1 over the image distance from behind the lens is equal to 1 over the focal point. Alright, now we're ready. I'll be showing you guys how to derive the equation for the far focal point, but you can actually apply this to using the same math to find your near focal point, and then you'll have your range. To calculate the far focal point in our depth of field equations, we first need to create a ray diagram.
In this case, our object plane is representative of the distance of the object we are focusing, but the near and far points represent the outer edges of everything in focus. One of the variables our final equation will be in terms of is the object distance p, meaning that it affects our depth of field. For this diagram, there aren't two rays meeting because of the way that we need to solve the equation. We specifically place one ray that is refracted through the lens at the farthest point still in the bottom half of the circle of confusion. It is the farthest point that still appears in focus. To start our derivation, let's rewrite the thin lens equation as p equals qf divided by q minus f. Also, we should note that q equals pf divided by p minus f, but we're going to save that one for later. Since pf and qf follow the same relationship as p and q with regards to f, we can say that pf equals qf times f divided by qf minus f. From the diagram we created, we see that qf equals q minus x. Therefore, we can substitute it in and we get pf equals q minus x times f divided by q minus x minus f. Just like with the hyperfocal diagram, we see that this one has similar triangles as well. Looking at these triangles, we can solve for x. First, we're going to get x equals c times q minus x divided by d, and then the 2's cancel out. And then we keep going and we get q times c minus x times c equals x times d. QC equals x times d plus c, and then we finally get x equals QC divided by d plus c. So we're going to input this back into the PF equation, and we get this. Oof, okay, that is a handful. So what we're going to do is factor out some of those q's to help us out a bit. We're going to get this. And we can now make everything within the brackets one fraction, and that's going to help us in a sec. So we get this. And now here's the key, multiplying by 1, but that 1 is going to be in disguise, of course, because multiplying 1 over 1 isn't going to really help us. So instead of 1 over 1, we're going to do d plus c divided by d plus c, and we're going to get this, q times d times f over qd minus f times d plus c.
So we have the equation for PF, which is really good, but it's actually in terms of some variables that aren't very practical. For example, image distance requires calculations using the thin lens equation, so we're going to actually input that into our equation. Furthermore, photographers and cinematographers work in terms of an f-stop or f-number rather than the actual diameters.
So we can actually use what we found earlier, q equals pf divided by p minus f, which we derived from the thin lens equation, as well as the standard formula that relates d, f, and n. And we're going to get this wild looking equation, and that kind of looks like it made it worse, but bear with me. Let's split it up. So first we have our numerator, and we have p times f divided by p minus f times f divided by n times f, and we're going to get, when we multiply that all out, this one's pretty standard, p times f cubed divided by n times p minus f. And now for our denominator, and this is where it gets super complicated. This is probably the hardest part of the equation of this derivation. So when we multiply out, we get this equation right here, and we're going to simplify that out a little bit to get this. And this is where we multiply out that binomial. I know it hurts. It's really painful to do. And then we have to painstakingly combine all of those terms to get f times f squared minus p times c times n plus c times n times f divided by n times p plus f. And when we combine that numerator and denominator, we're going to have that n times p minus f factor out, and then we get p times f squared divided by f squared minus p times c times n plus c times n times f. So
PF equals P times F squared divided by F squared minus C times N times P minus F. There we go. We have the far focal point in terms of the object distance, P, the focal length, F, the circle of confusion, C, and the F number, N. But wait, remember how I talked about that hyperfocal distance before? So if we have that distance, we can simplify the equation even further. Rearranging the hyperfocal equation, we get F squared equals C times N times H minus F. We already have two instances of F squared that we can substitute into the equation that we just found for PF equals P times C times N times H minus F divided by C times N times H minus F minus C N times P minus F. And we're going to simplify that all out to, as you can see, let's do this step right here. And then we get PF equals P times H minus F divided by H minus P.
Also, because of what we know about the hyperfocal distance, we can say that the depth of field far point is equal to P times H minus F divided by H minus P when P is less than H, and infinity when P is greater than or equal to H, since for lenses focused at the hyperfocal distance and all distances after, the range of focus will always extend to infinity.
Alright, so that's how you find the far focal point. I've left out the super nitty-gritty algebra, so feel free to go back and write out all the steps for yourself. It was really helpful when I was first creating this. To find the near focal point, we use a diagram like this with these similar triangles, and well, I'll leave the rest up to you.
To combine our two solutions and get the actual equation for depth of field, since depth of field is defined as the range of focus, we subtract the near point equation from the far point equation. Just like before, the range of focus will extend to infinity when the image is focused at the hyperfocal distance and anything after that. When we combine both of the diagrams, it looks like this. Any object placed from here to here will fall within the circle of confusion defined range of focus.
So, yeah, thank you so much for watching.